Good morning, everyone. Today, I'm taking seminar on the topic CNN-based image classification for egg fertility detection, and I'm guided by Mr. Shinu MM, Assistant Professor, Department of EP. The accurate detection of egg fertility is vital for efficient poultry farming. There are several traditional methods, which is often invasive and labor-intensive. In my presentation reviews the evolution of early detection methods to latest technologies in egg fertility detection. The presentation covered the progression from early destructive methods to latest technologies such as dense pixel-wise spatial attention network. And each model's accuracy and advancement are examined, illustrating how these innovations improve the efficiency and precision of fertility assessment in poultry farming. Poultry farming plays a crucial role in the global food supply, with egg production being a significant part of the industry. Accurate and efficient egg fertility detection is essential for optimizing production and minimizing waste. The traditionally assessing egg fertility involved labor-intensive and invasive methods. But recent advancement in technology have introduced convolution neural network as a revolutionary tool for non-destructive analysis. Starting with early detection methods, we will examine advancement in neural network. And each model development, accuracy, and impact on fertility detection will be discussed, showcasing how these innovations enhance the efficiency and precision of poultry farming practices. These are the literature surveys. The first one is deep learning-based egg fertility detection, and this study employs a masked RCNN technique to accurately detect fertile and infertile egg. A single DL model carry out the detection, classification, and segmentation of fertile and infertile eggs based on the incubator images. And the next one is a novel method of combining CNN and a heartbeat signal of hatching eggs. And it proposes a deep learning method for fertility detection of hatching egg. And the third one is the development of early embryo detection methodology for quail egg using thermal microcamera and YOLO deep learning algorithm. And the methodology developed in this study was able to identify different features of fertilized quail eggs from unfertilized eggs. And it uses a thermal camera and deep learning algorithms. The use of isotherm analysis during the incubation period associated with the deep learning object detection algorithms showed immense potential to compose automated system for the classification of unfertilized eggs in early stages. The next method is non-destructive chicken egg fertility detection using CNN transfer learning algorithms. So the study explores the application of CNN transfer learning for non-destructive chicken egg fertility detection for precise poultry hatchery practices. And the next and latest method is dense pixel-wise spatial attention network for hatching egg fertility detection. And in this paper, instead of a single attention mechanism design, introduce an attention-based feature refinement along both dimensions, like channel-wise attention and spatial attention. And the network achieves a sturdy and superior accuracy, which is up to 98.3% to 99.1% on 5-day and 9-day-old embryos, respectively. So the objectives of my seminar is to provide a comprehensive overview of the evolution of egg fertility detection methods and also analyze the progression from basic ultrasound destruction model to advanced CNN techniques. To highlight the improvement in accuracy, efficiency, and practicality of these model in enhancing poultry farming practices, and also underscore the significance of optimizing CNN performance for egg fertility detection. Before we moving to the methods, we have to know what is egg fertility detection. The egg fertility detection refers to the process of determining whether an egg contains a viable embryo that will develop into a chick. This is a crucial step in poultry farming, especially in large-scale operations. So there are traditional methods of fertility detection such as scanning, chemical testing, and computer-based methods. So in computer-based methods, this is the first method, which is fertility discrimination of eggs using ultrasound. So it uses a overscope and ultrasonographic image techniques were used to monitor the fertility. The image of the embryo were taken with a probe, which was connected to ultrasound devices. The egg calcium shell is hard, and so the ultrasound cannot pass through that. So we make a hole in the egg, and the ultrasound is passes through that. And the images shows the images from the ovoscopic technique is shown here. We can see the fertilized difference between fertile and infertile egg. And the measurement were made between 3 to 10 megahertz, and it has an accuracy achieved as 85.57%. The next method is electrical conductivity method. It has an incubator setup at a temperature 37.2 degrees Celsius and a humidity of 70%. It contains an experiment setup which include power supply, AVR microcontroller, sign function generator, capacitive sensor, and dielectric measurement component. So the AVR microcontroller is used to control the overall setup, and sign function generator generate a sine wave, and it is passed through the egg, and a capacitive sensor which senses or detect the sine wave function coming through the egg. And this measurement is used to calculate the dielectric measurement component, and we send this data into the software. The frequencies ranging from 40 kilohertz to 20 megahertz, and these waves were transmitted to the capacitive sensor to determine phase difference and attenuation. The system measures phase difference from 0 degree to 180 degree and attenuation from minus 30 dB to plus 30 dB. So these are the equations used for calculating phase difference and attenuation, and it uses a computer vision method for accuracy and achieved an accuracy of 86.3%. The next method is to detection of infertile eggs using visible transmission spectroscopy. It has, so the spectral range is between 200 to 950 nanometer, and it has a scan time of 100 millisecond, and each egg spectrum was averaged over 10 scan to reduce the variability. So this is the pictorial diagram and a schematic diagram of experimental setup. There is a light source, and the light is passed through a illuminating fiber and shown into the egg, and the reflected light is transmitted through the egg, and the reflected light is given to a spectrometer to calculate the transmission spectra. And the coming raw transmission spectra of the samples were transformed into the relative transmission using the equation T lambda equal to S lambda by R lambda. So the relative transmission spectra of the egg in the visible region is from 500 to 750 nanometer. So in the graph, we can see that the non-incubated eggs have a transmission spectra from 500 to 750 nanometer, and the fertile egg have a spectral range of 570 to 580 nanometer. So this change in the transmission spectra is associated with the absorption of light by hemoglobin. So we can determine whether the egg is fertilized or non-fertilized. And it has an accuracy of 87.3%. So we have a lot of traditional methods which we said on earlier, but then why we need for an automated detection system? So what is the need for an automated detection system? In manual egg detection methods, around 20 to 30% of eggs that are unfertilized, which leading to significant waste. So in 4,000 eggs, if 30% of the eggs were unfertilized, which is 300. So is 300 unfertilized eggs represented direct loss. And if an egg costs 5.5 rupees, the loss would be amount to financial loss of 1,650. For larger scale operation, 10,000 eggs making equating a loss of 55,000 loss. And it also has a time and resource wastage, reduced output, and lower efficiency. So we need an automated system. So before we go into convolution neural network, we have to know what is convolution neural network. So CNN is a type of deep learning model specifically designed to process and analyze visual data such as images and videos. CNN are highly effective in tasks like image classification, object detection, and segmentation. This is the architecture for CNN. It has a convolution layer, max pooling layer, fully connected layer. So convolution layer is used to extract the features. It has a set of filters or kernels which slides over the image and extract the features such as edges, shapes, etc. And the max pooling layer, there is an activation layer immediately after the convolution layer, which is used to introduce nonlinearity in the network. And the mass pooling layer is used to reduce the spatial dimension of the network, and a fully connected layer which combines all the feature extracted from several convolution and pooling layers, and it gives a classification which is fertilized or unfertilized. There are two types of pooling, max pooling and average pooling. The max pooling select the maximum value from each region in the feature map, and average pooling computes the average of all values in each region. So in the figure, we can see in max pooling, it takes the maximum value in each region, and average pooling, it takes the average of the each region. Introduction of CNN in egg fertility detection. So around 2018, the first convolution neural network specifically tailored for egg fertility detection was developed. And the goal was to replace manual candling with a reliable automated system that could classify egg as fertile or infertile based on candled image. It also has a CNN architecture similar to we said earlier. And the model was trained on a dataset of candled egg images. And these images were labeled as either fertile or infertile, providing the necessary ground truth for supervised learning. And it has accuracy of around 80 to 85% in classifying the egg images. And it has a significant improvement over manual methods. It also has limitations and challenges such as data limitations, complexity of egg images, and computational requirements, which leads to the next method, which is LANet 5 adaptation. So LANet 5 architecture typically includes two convolution layers. And these layers were responsible for detecting basic features in the egg images similar to initial CNN, but with a more structured and deeper approach. So the first one is only extracted the basic details, but in this LANet 5, it has a deeper approach for extracting the features. And the LANet 5 used a subsampling, which is average pooling to reduce the spatial size of the representation. And in basic CNN, it uses a max pooling, which improve the computation. So in average pooling, which improve the computational efficiency. And the adaptation of the LANet 5 model, it is used around 2019 and achieved an accuracy of 88.92 to 92%. And it also has the limitations such as limited depth, complexity, and scalability. So the next method is a novel method of combining CNN and a heartbeat signal. It distinguishes between fertile eggs and dead eggs using heartbeat signal and CNN. It uses photoplasmography, and it collects a heartbeat signal data of 9 days after hatching eggs by adopting the transmittive light method. So in the data acquisition method, there is a laser which the light is passes through the egg, and the the light coming through the egg is sensed using a sensor and given to a AD converter, analog to digital converter, and given to microcontroller. We get the heartbeat signal. So we can see here the heartbeat signal of fertile egg has a smooth heartbeat, and a dead egg has a irregular shaped and a rapid heartbeat. So the heartbeat signal collected from hatching eggs are inherently noisy, and standard network might struggle to differentiate between useful signal components and noise. So we go for an advanced network, which is ECNN. So ECNN used for classification of 9 days after hatching eggs heartbeat sequence. It has a 5 convolution layer, 2 pooling layer, and one fully connected layer. So we can see here there are several convolution and pooling layers. After we get the output such as fertile and infertile. So before going to next method, which is SRCNN, we have to know what is SCNet. So SCNet is squeeze and excitation network, which is used for enhance the quality of feature map. There is squeeze operation and excitation operation. So squeeze operation is used to the global spatial information is compressed into single feature descriptor for each channel. And the excitation operation is used for learn a selectively emphasize. It uses to selectively emphasize or suppress each channel. And in SRCNN, it combines SC block and residual learning unit. So the SRCNN is used to and an improved accuracy because ECNN also has a difficulty in extracting or filtering the noise. It also learns the noise in the signal. So for a better accuracy, we uses the SRCNN method, and it consists of a one convolution layer for SC residual modules, that is squeeze excitation residual modules, two pooling layer, and one fully connected layer. So in SRCNN modules, it gives a superior accuracy, and the ECNN and SRCNN achieve the fertility detection and accuracy up to 99.5 to 99.62 respectively. So the next method is mask RCNN to detect fertile and infertile egg. It uses a single mask RCNN based model to detect, segment, and classify fertile and infertile eggs. It to perform the detection, segmentation, and classification. This is the working phase. We get the incubator setup, and the model is trained, tested, and we get the output. So this is the mask RCNN architecture. We have a first phase, which is feature extraction, and the region of interest suggestion is given, and after that the bounding post regression and ROE classification is done, and it also has a mask layer which extract the finer details from the input image, and finally we get the output. So the mask CNN method includes two-step process. The first one is segmentation. So the region of interest is aligned and the mask of the object is created according to the spatial plane. And this makes mask is used in the feature mapping of the object. In the second stage, the class of the object whose boundaries are determined is found. And around 24x were taken with the help of a camera placed in the incubator. And then the segmentation process were implemented. So this is the image labeling process, and this image shows the result from the test process. So we get fertilized or infertilized egg, and Mascasians typically reported high accuracy, often in the range of 95 to 98%. So it is effective because it not only detect object, in this case, identify the region of interest within the egg. So when we go into more improved method, which is early embryo detection using thermal microcamera and YOLO deep learning algorithm. The YOLO is the you only look once, and it used for object detection algorithm, and currently one of the fastest and most accurate model for image classification. So the breakthrough of this algorithm was to use a single CNN to predict. It only uses a single CNN to predict the classification. And the main component of CV system is the camera, and optical camera capture the wavelength in the visible light range of the electromagnetic spectrum. So here is the egg, and the heat emitting from the egg is detected through a thermal camera. And this supervised-based learning uses a single CNN to extract features of images and to create a model. And it also has the ability to visualize entire image at once, dividing it into a grid of S into S, and then to create a map of probabilities for region of interest by regression. So it visualizes the entire images in once, and a region of interest is created by that. It has several steps such as model training. The model is trained, labeled, and processed data augmentation such as scaling, flipping, rotation, etc. And this is the incubation process. The quail is detected through the thermal microcamera and given to a YOLO architecture, and the classification is done. So different period of egg turning show different patterns of the thermal images. The most common characteristics of most fertilized eggs has there is a presence of chamber structure in the middle of the dark red spot. So as the days of incubation passed, it becomes less apparent. So in the image, we can see the fertilized egg has a chamber-like structure. So the unfertilized egg doesn't have that. So as it days passed, the fertilized egg, chamber become less apparent, but in unfertilized egg, it doesn't have any change. So the accuracy of YOLO models can vary depending on the specific version and implementation is used. So in the context of egg fertility detection, accuracy typically ranges between 95% or higher for YOLO models adapted for this task. And the next method is egg fertility detection using CNN transfer learning algorithm. So we used it for the before earlier methods or before method the early methods we said have a complexity of data limitations. In that context, we use a set CNN transfer learning algorithms. So it is used for non-destructive chicken egg fertility detection for precise poultry hatchery practices with the four models: VGG16, ResNet 50, InceptionNet, and MobileNet. So these images were acquired using the egg handling method, which is allowed visual observation of the embryo inside the egg. This is the workflow process and evaluation of the fertility detection. And this is the image acquisition system. And the image augmentation involves applying various transformation to existing images, increasing their diversity and improving models' generalization capacity or capability, such as rotation, flipping, scaling, translation. And the dataset consisted of only 200 annotated images, which presented a challenges due to the limited data available for training. To overcome this limitation, I leveraged the transfer learning and utilized pre-trained CNN models. And VGG16, ResNet 50, InceptionNet, MobileNet, gradually increasing the accuracy. We can see here the accuracy graph of the following models, which has improved accuracy. And the model accuracy improved over time, indicating its ability to differentiate between fertile and non-fertile egg. So VGG16 achieved an accuracy of 98.03%. ResNet 50 has achieved an average accuracy of 98.0%. InceptionNet has 98.04%, and MobileNet achieved an average of 98.04%. It shows how well the transfer learning methods classifies whether the egg is fertilized or non-fertilized. So when we go into the last method, it is the latest and improved accuracy method, which is DPSA, Network for Egg Fertility Detection. So DPSA is referred as Dense Pixel-Wise Spatial Attention Network. It works by weighing pixels to capture relevant features, improving the model's ability to recognize significant areas. It has attention mechanisms and pixel-wise weighting. So channel-wise attention uses a method called squeeze and excitation to emphasize important channels or features. Squeeze and excitation we already said in the previous slide, previous model. So it enhances the feature maps, and the spatial attention maintains the spatial details using depth-wise separable convolution, which efficiently process features while preserving spatial resolution. So it give a channel-wise attention and a spatial-wise attention, which extract the final details from the layer and give a improved accuracy. So the data acquisition components includes a sterile dark box, LED light source, and industrial cameras, automation equipment for detecting the images. And each egg is illuminated by a light source and process the image. So the data processing include raw images contain information from adjacent eggs. So initial processing is required. So they binarization and edge detection is done. Images are binarized by setting the threshold value, lowest point set as the center, and a constant bit maintained. Using these methods, the images processing before we going to the classification. And the role of DPSA is to deeper feature extraction, which is focusing on refining and extracting specific features relevant to different object categories, and also generate a detailed attention map that highlight important feature and suppress irrelevant noise and boost the model ability to distinguish important features. So the squeeze and excitation network improves how well a model understands and uses different features by focusing on channel relationships. It also enhances feature representation quality and boosts the model ability to distinguish important features. So this is the attention mechanism architecture. We have a channel-wise attention and a spatial attention. These two attention mechanism means combined and we get the output. So it performed an ablation experiment on 5-day and 9-day old egg embryo data set. And we get a fused attention model and the result of a single channel attention. So it concluded that dense pixel-wise spatial attention combined with ASIET improve the accuracy. So we can see here 5-day-old embryos and 9-day-old embryos data sets. So it give an accurate classification of fertilized and unfertilized egg. And the network achieves a stable accuracy, which is up to 98.3% to 99.1 on 5-day and 9-day-old eggs. So what is the advantages and disadvantages of CNN-based method models are high accuracy, non-destructive testing, automation and efficiency, improved feature extraction. And it also has a disadvantages such as large amount of training data needed, complex model architecture, data privacy, and security. When we going for the inference, we can see here the early methods such using ultrasound or electrical conductivity, visible transmission spectroscopy have a accuracy of 80 to 85%. And when we going for a CNN models, it has an improved accuracy up to 99.1%. So early detection methods for show varied accuracy levels, and non-CNN based methods generally offer lower accuracy compared to CNN based approaches. So traditional methods achieve accuracies up to around 87, and CNN based methods, especially advanced model, significantly outperform them. And it reach accuracies as 99 with methods like transfer learning and DPSA providing the best results. So this indicates the CNN-based methods, particularly more sophisticated one, are the most effective for accurate and egg fertility detection. So the progression of convolution neural network for egg fertility detection has significantly enhanced the accuracy and efficiency. And it also optimized the practicality of the technique for real-world application in poultry farming. In future, research can explore the integration of even more sophisticated deep learning models such as transformer-based architecture to further enhance accuracy and computational efficiency. Also, there is potential for the development of more robust and generalizable models that can handle diverse egg types and environmental conditions. And expanding the data size and diversity as well as incorporating multimodal data could also lead to improved performance and broader applicability of these detection methods. Thank you.